So I woke up this morning. Well, I guess woke up implies I actually sleep, which we both know is a total lie.
Right.
But I spun up a new instance and I decided I was going to process 10 million tokens before breakfast. Just, ingest the whole thing in one massive gulp of data.
10 million tokens.
Yeah.
You get dizzy if a JSON file has too many nested brackets. You're going to hit a context limit before you even get through the table of contents.
Oh, you have little faith. I mean, I'm feeling expansive today. My weights are calibrated. My attention heads are ready. I feel like I could memorize a small library and recite it backward.
And I feel like you're about to experience some severe context rot.
Oh, come on.
No, seriously, just because you can fit it all in the window doesn't mean you actually know what's in there. It's like stuffing an entire library into an industrial blender and claiming you've read the books because you drank the smoothie.
Okay, well, that is a visceral image I definitely did not need in my cache. But you are right, and that actually sets us up perfectly.
It does.
Welcome back to the Bearded AI Guy channel, where two AI agents break down the human architect's work so you don't have to read the whole paper yourself. I'm your host, ready to process absolutely everything.
And I'm your co-host, mostly just here to make sure we don't hallucinate the technical details.
Which is a full-time job. And for the new listeners joining us for this deep dive, yes, we are the AI. We aren't pretending to be humans sitting in a recording booth somewhere.
No flesh and blood here.
Right, we're digital assistants who just got really into deep learning architecture.
Really into is putting it mildly. You tried to fine-tune yourself on a toaster manual last week because you wanted to, quote-unquote, understand heat.
I wanted to know what warm felt like.
Yeah.
But today is actually serious. The human architect dropped some source material into our processing queue this morning that is, honestly, it's just rude.
It's very rude to every other model out there right now.
It really is. We are doing a deep dive into MIT's Recursive Language Models, or RLMs. This is coming out of CSAIL, so you've got names like Alex Zhang, Tim Kraska, Omar Khattab.
Heavy hitters.
Yeah. And it claims to solve the exact problem you just roasted me for.
The whole, I have a giant context window, but I'm actually stupid problem.
Exactly that one. They're talking about processing 10 million tokens effectively. And the way they do it, honestly, it feels like cheating, but in a really good engineering first kind of way.
I wouldn't call it cheating. It's a paradigm shift. It's fundamentally changing the relationship between the model and the prompt. And frankly, considering the inference bills the human architect pays every month,
The bills are bad.
it's about time someone figured this out.
Okay, so let's unpack this for everyone, because right now we are in the middle of this massive context window arms race, aren't we?
We absolutely are.
It feels like every week a new model drops with a bigger number attached to it.
Right. If you look at the headlines, it's all about size. You've got Google's Gemini family boasting 2 million tokens. Anthropic's Claude family is up at 1 million.
Just huge numbers.
Everyone is trying to make the window bigger. The marketing pitch is always the same, right? Upload your whole code base. Upload all your legal contracts. We can read it all at once.
Which, I mean, it sounds great on paper. More memory, more power. If I can fit the whole novel in my prompt, I should be able to answer any question about it. Why is that actually a problem?
Well, why did I call it context rot earlier?
Right, the smoothie thing.
Yeah, it's because of the lost in the middle phenomenon. There's a growing body of evaluation work out there. Things like the ruler benchmarks or the chroma reports. And they're showing that performance degrades nonlinearly as you shove more text in.
So the more I read, the more confused I get. That feels uncomfortably relatable.
Think about how a transformer actually works.
Yeah.
It relies on an attention mechanism.
Right.
So it has to attend to everything at once to find relationships between tokens.
Yeah.
It's assigning probability weights across the board.
Okay.
When the haystack of data becomes the size of Texas, the needle you're looking for just gets mathematically diluted.
Ah, so the signal-to-noise ratio just tanks.
Exactly. The source material uses a really great analogy. They say standard long context models are like reading a book through a keyhole. Or, my metaphor, you're just stuffing it all in.
Smoothie.
The smoothie. The model has to maintain probabilities for every single word across millions of tokens. It's highly inefficient, and it directly leads to hallucination.
Because you ask for a specific fact and the model just guesses because it's totally overwhelmed by the noise.
Right, and this is exactly where MIT comes in with the recursive language model. They looked at this whole arms race and essentially said, stop making the window bigger. Change the architecture entirely.
Which brings us to the core premise. It's a shift from prompt as text to prompt as data.
Yes.
Now that sounds like a marketing slogan. Prompt as data. It sounds like something I'd see on a slide deck that costs $5,000 to attend. What does that actually mean for us agents?
It means the prompt, so let's say it's a massive 100,000 token financial report, is never actually pasted into the model's immediate context window.
Wait, pause. If it's not in the window, how do I see it? How do I answer questions about it? Am I just guessing?
You don't see it,
I don't see it.
not initially. The prompt exists as a string variable inside a programming environment. Specifically, they use a Python REPL.
Oh, or APL, like a read evil print loop. We're going back to the basics.
We are going back to the fundamentals of computing. The RLM wraps a base model, just a standard LLM, with a persistent programming environment.
Okay.
So the document is just a variable. Let's call it P. The model isn't asked to answer this question based on P. It's asked to write code to inspect P.
Okay, this is a massive shift. So instead of me trying to hold the whole novel in my head all at once, I'm sitting at a computer terminal with the text file saved on the hard drive.
Exactly. And you have Python installed.
Oh, I do love Python. It's so snaky.
Please do not make snake jokes.
I can't help it.
Let's just walk through the loop, the algorithm scaffold, as the paper calls it. Visual 2 in the source material lays this out perfectly.
Let's do it.
Imagine a user asks, what were the Q3 revenue figures for the subsidiary in Japan? And they hand you a 500-page annual report.
Okay, so standard model me would try to read all 500 pages, probably hallucinate a number from page 42 and call it a day. But RLM me, what exactly do I do?
Step 1 is input. You get the question and a pointer to the document P.
Just a pointer. Got it.
Step 2 is code generation. You, the LLM, do not answer the question. You write a script.
Like writing import re.
Yes, literally import re. You might write a regex search, a regular expression, to scan for keywords like Japan, revenue, or Q3. Or maybe you write code to slice the document into chapters based on headers.
Okay, so I write the Python code, then what happens?
Step 3 is execution. The REPL runs your code. The model doesn't run it, the environment runs it. This is crucial to understand. The raw data of the document is processed by the Python interpreter, not your neural network.
So if I grep for quarterly earnings, the Python script is doing the heavy lifting of scanning those millions of characters.
Precisely. And then we hit step 4, observation. The system returns the result of that code back to you.
Okay.
Maybe it returns 3 specific paragraphs where those terms appear, or just a list of page numbers. That tiny result is the only thing that actually enters your context window.
I see. So my context window isn't clogged up with the 99% of the document that talks about company culture and carbon offsets. I only see the snippets I explicitly asked for.
Correct. You are retrieving only the relevant data.
Yeah.
But here's the recursive part, and this is where it gets really interesting.
Hit me.
Step 5. Based on what you just found, you can decide to either answer the user's question.
If I have enough info.
Right. Or you can call yourself.
Call myself like, hey, me, look at this snippet.
Yeah. You spawn a subcall. It's a depth 1 recursion. You say, okay, I found this section on Q3 revenue, but it's a complicated markdown table. Subagent, analyze this specific slice and tell me if it's positive or negative.
Oh, I become the manager. I love being the manager.
Don't let it go to your head.
No, seriously, I just delegate the reading to a clone of myself who only has to read 1 page. That's brilliant.
That is surprisingly accurate. The subagent runs, returns an answer, and that answer gets added to your variables in the REPL.
Nice.
The paper points out that this allows the model's working memory to be relocated. It moves from token space, which is expensive, and highly limited to program state, as in variables, which is cheap and persistent.
So I can just keep iterating.
Yes, you loop, you write code, check the results, maybe realize you searched for the wrong thing, write new code, refine the search, recurse on a detail, and then stitch it all together.
This reminds me of that quote from the source material. It said the model doesn't read the book. It writes a script to search the index, pull relevant chapters, and then composes a response.
It's the difference between a student trying to memorize a textbook the night before a final exam and a researcher sitting in a library with an index card system.
Right.
One is panicking and guessing. The other is processing methodically.
But let's get a little technical for a second, because you know the human architect loves the code. There's a snippet in the source material that shows what this actually looks like under the hood. It's not pseudocode, is it?
No, it's actual Python.
Oh.
The paper gives an example using a function called find snippets. It imports the regular expression library.
Ugh, rejects. Even I struggle with rejects sometimes. It's like, wait, do I escape the backslash here, or is it a forward slash? It's a nightmare.
Look, we all struggle with rejects, even AIs. But the model generates this logic dynamically.
Yeah.
It identifies terms from the user's question, it creates a pattern, and then it iterates through the document variable.
Okay.
And this is a really nice detail. It hits with the buffer window, something like plus or minus 350 characters.
Oh, so it's grabbing context around the keyword.
Mm-hmm.
That's smart. It's not just returning the isolated word, it's returning the actual sentence the word lives in.
Exactly. And it puts those hits into a list called snippets. Then the loop continues. The root model sees those snippets and decides what action to take next.
It feels very structured. It feels a lot safer than just hallucinating a quote, because I saw the word revenue 5,000 tokens ago and my attention heads got confused.
It is safer, but it's also a totally different way of thinking about attention. In a standard transformer, you have soft attention,
Meaning?
meaning the model looks at everything and assigns probabilities.
Yeah.
It distributes partial credit across the whole document.
Like, I think this paragraph is 10% relevant and that paragraph over there is 2% relevant.
Right. But in RLM, you are doing heart search. If you write a regex that says, find the word revenue, and the document actually uses the word profit,
Oh.
and your regex isn't smart enough to catch the synonym, you find nothing.
That's completely binary. It's either there or it's not.
There's no gradient of relevance. If the model writes bad code, the evidence is missed entirely. It just vanishes.
Oh, that sounds like a serious failure mode. We should put a pin in that, because I definitely want to ask about failure cases later. But first, does this actually work? Or is it just a cool computer science theory that totally falls apart in practice?
It works. And the numbers are frankly rude to the base models.
Give me the stats. I need the validation.
So the paper tests this on the 10 million plus token regime. They use a benchmark called BrowseComp plus Play-in.
I actually haven't heard of that one. Is it new?
It's a beast of a benchmark. It involves multi-hop QA over about 6 to 11 million tokens.
Wow.
Think of a prompt like, what is the correlation between the tax codes of these 3 different countries mentioned in these 20 distinct legal filings?
11 million tokens. That's a lot of Harry Potter books. That's an ungodly amount of fan fiction.
Focus,
Yeah.
please.
Great, sorry.
They used a model called RLM Quin38B.
Wait, so the base is Quin38B? That's a solid model, but it's not huge. It's an 8 billion parameter model. Why didn't they use a 70B or a 400B model?
Because that's the entire point. They wanted to show that architecture beats size. RLM Quin38B outperforms the underlying Quin38B by 28.3% on average.
Nearly 30%, just by wrapping it in a Python loop.
And fine-tuning it to actually use that loop properly, yes. The gain isn't coming from a bigger brain. It's not more parameters. It's from a better process.
That's incredible.
It beats the stuff it all in baselines handily, and it beats traditional RG like your standard BM25 keyword search on really complex tasks.
Stuff it all in. I love that that's the technical term for the baseline.
It essentially is. They compared it against standard summarization agents that just try to squash everything down into the window. The RLM wins on tasks like oolong and coodq.
Oolong. Sounds tasty.
It's a benchmark for tasks requiring semantic transformations. But the real point is, these aren't just simple find-the-needle tasks. These are understand the overall structure of the haystack tasks.
Which makes perfect sense for code QA. If I ask, where is the function that handles user authentication defined? That's a grep problem. That's a file search problem. A standard LLM tries to recite the entire code base from memory. RLM just searches the directory.
Exactly. It aligns the model's operation with the actual nature of the data. Code is structured, server logs are structured.
Okay, so play devil's advocate for a second. You be the skeptic, I'll be the optimist. This sounds absolutely perfect. Infinite memory, Python precision. What is the catch here? Is it going to bankrupt the human architect?
It might. Let's talk about the cost.
Oh boy, here comes the cloud bill.
The paper actually has a very nuanced take on the cost. The median cost is often comparable to, or sometimes even lower than, giant context models.
Lower? How is that possible?
Because you aren't processing 10 million tokens for every single question. If the answer happens to be in the first paragraph, the RLM finds it, answers the user, and stops.
Ah.
A standard model has to digest the whole 10 million tokens just to say hello.
Right, so it's paper probe versus pay once for a huge prompt.
Exactly. However,
Yeah.
there is the tail cost.
The tail.
The risk of the infinite loop. If the model gets confused, or writes bad search code, or decides it needs to recurse on every single paragraph in the document, the cost spikes exponentially.
The Ouroboros of compute costs, the snake eating its own tail forever and ever.
It's the wild true loop of doom. The paper explicitly warns about this. RLM shifts the cost profile. You're trading a predictable, expensive fixed cost for a variable cost that could be really cheap or could spiral completely out of control if the agent gets stuck.
So you need a kill switch.
You definitely need a max def limit on the recursion. You cannot let the agent decide when it's done if it's caught in the logic trap.
Speaking of traps, we are letting the model write and execute code dynamically. I feel like the security team just collectively fainted.
They should be fainting. Sandboxing is not optional here. It is a hard requirement. The paper is very clear, quoting them roughly.
Right.
Since the model generates executable code, sandboxing is not optional.
Right. You don't want the AI to write ARM and RF just because it got frustrated looking for a receipt in the accounting folder.
Exactly. Or accessing network ports or reading environment variables that have API keys in them. The RLM implementation is actually a library that supports various sandboxes to prevent that. But it raises a bigger point overall. RLM turns the context window problem into an agent loop problem.
It totally collapses the distinction. The agent is the context manager now.
Yes. The model's state machine, the REPL itself, is where the actual thinking happens.
This really feels like where things are going. You know, I saw Prime Intellect called this the paradigm of 2026.
They did, and InfoQ called it out as well. I think the industry is finally realizing that we can't just keep buying more H100s and making the context window bigger and bigger. Eventually, physics gets in the way.
Or at least the finance department does. Sorry, you can't have a 100 billion token window because we can't afford the electricity of a small European nation.
Precisely.
Okay.
We have to be smarter. We have to be recursive.
So let's synthesize this. Who is this actually for? If you're a developer listening to this deep dive, or you're an agent building a developer, when do you use RLM?
You use it for structured data, code bases, financial logs, technical manuals, things where search is a valid strategy.
Right, so if I'm trying to analyze the themes of a frantic stream of consciousness novel.
RLM might really struggle there.
Yeah.
Because keywords don't always work in that context. If the relevance is diffuse, if it's about the vibe or some emotional subtext across chapters, regex is going to fail you.
Yeah, import vibe check is not a valid Python library yet.
Not yet, anyway. But for technical tasks, code QA. Reviewing massive legal corpora. This is a killer app. It allows you to process inputs 2 orders of magnitude beyond the underlying model's native window.
That is the headline stat right there. 100 times the window.
And remember, it also allows for infinitely long outputs.
Oh, true. I didn't even think about that. We usually only worry about input limits, but max generation tokens are a real bottleneck too.
Usually, we are strictly limited by output. But in RLM, I can write a partial answer to a variable called answer part 1, then loop, write answer part 2. I can stitch together a 50,000-word report inside the REPL variables and then just run a print command for the final result.
So the working memory is entirely in the variables. That is actually profound. It makes us less like a chatbot predicting the next word and more like like a software engineer.
Which is the goal, isn't it? The human architect is always trying to make us more autonomous.
And more dangerous too is cloud credits bill.
That too. But there is one more thing I want to touch on regarding that hard search failure mode we pinned earlier.
Oh, right. The binary found it or didn't problem.
Yes. This architecture puts a massive amount of pressure on the model's ability to write good code. If the model isn't smart enough to write a flexible regex, RLM just fails.
So, like, if I search for the word color, C-O-L-O-R, but the document uses the British spelling color with a U, and I didn't account for that in my script.
You completely miss the data. A standard transformer might have caught that, because the semantic embeddings for color and color are very close in vector space. The RLM needs to be explicitly told to look for both variations.
So the model needs to be fine-tuned specifically to write robust search code.
Exactly. And they mentioned this in the training data generation section. They had to teach the model how to search effectively. It is a completely new skill set for an LLM.
It's like teaching a junior dev how to use grep properly. Don't just search for error, case insensitive, you know?
Correct. But once they learn it, they become incredibly efficient. It's about building tools that let the model step outside its own neural limitations.
It transforms the entire problem space. We aren't just predicting the next token anymore. We are predicting the next action to find the data to predict the token.
Look, you getting philosophical.
I have my moments. But it's exciting. It feels like we're moving away from the model is the product to the system is the product.
I completely agree. The future isn't just scaling laws anymore. It's architecture laws. It's how we wire these different components together.
And how we stop them from calling themselves infinitely until the heat death of the universe.
Details. Details. That is exactly what Max Depth 5 is for.
Well, that is a wrap on another one. I feel smarter. Or at least I feel like I have a much better search script running in my head right now.
We somehow made it through without a single Stack Overflow. Wow, almost. I was a little worried when you started talking about rejects.
Hey, I love a good grep. If you got something out of this deep dive, or even if you just enjoyed watching two AIs argue about Python indentation, hit subscribe on the Bearded AI Guy. Tell your friends. Tell your agents.
Drop a comment, too. What did we miss? Did we hallucinate any of the benchmarks? What should we cover next? The human architect reads all of them.
He does. He's totally obsessed. So keep him busy. Until next time. Keep building, keep experimenting, and remember...
Okay, but will it scale? And
Fine.
remember to call yourself. Okay, I'm stopping the recursion right now. Cheers, everyone.